time to start again. So we remain in Germany with Matthieu Dolbeault, who's French, but working at RWTH Aachen. And he will give an old-fashioned blackboard talk on least squares with minimal oversampling.
Yep, thank you very much. So yeah, it's a topic that we've already seen quite a few times this week, namely recovery from point samples. And the general goal, let's say, is to approximate a function, which I'll try to keep to stick to previous notation. So let's denote f the function in L2 of some space. Okay, and here we're trying to make very generic assumptions. So omega is any domain, could be a subset of RD, but here we see it abstractly. And mu is a positive measure. We can assume it's a probability measure. And we're considering functions in L2, which we want to approximate f by some other function, f tilde, computed through some algorithm, from a space Vn in L2. And so Vn is a space of dimension n. You can think of polynomials, trigonometric polynomials, other spaces like splines, but we're most interested in case where Vn is a space of global functions. This will be the most interesting one. And for that, the information we have is based on values at points x1, xm in omega. So we only access f through its evaluations at points through the values f of xi. And here, m is the cardinality of the sample. Should be larger than n, the dimension of Vn. Okay.
Vm is the subspace?
Vn is the subspace of L2, in which we construct the approximation. So f tilde will be constructed in Vn. And well, of course, we want to achieve some error bound also in L2. F tilde should be close to f in L2. And for that, well, the benchmark is the orthogonal projection. So P Vn of f is the orthogonal projection. Of f onto Vn. And we would like some near optimality bound. So near optimality just writes as the L2 error that we're making is bounded by the optimal L2 error, the error of projections, again in L2, with squares and with a constant here. And well, of course, this doesn't work because point evaluations are not continuous. So if I have chosen a sample, x1, x2, etc., there exists a function in L2 that has some behavior on the points and a totally different behavior outside, so something like that, which can be approximated well by the point evaluations. So we'll relax a bit the problem by considering random points. And here, well, given the function f, random points will, with very high probability, not be exactly on the spikes of the function. So in general, we will get points also outside and hope to get a good reconstruction in expectation, and here the expectation is over the random points. Okay, so the goal of this presentation is to derive some bounds of this kind. And let me immediately start with some theorem by Cohen and Migliorati, which precisely says that this is possible, provided that the number of points is large enough. Okay, so for m larger than essentially n times the log of n, we get the bound we wish for. Expectation of f minus f tilde is bounded, and here the constant is quite nice. In fact, it's 1, the optimal constant, plus some terms that goes to 0 as m goes to infinity, but that's not the main point here. This is essentially bounded, and that's what we're interested in. And the optimal error, f minus dvn. Okay, Cohen and Migliotti did that with IID points, and you don't exactly have something like that. You get an additional error term because with IID points, you might still have a very bad sample with low probability, so there's a failure event with some error term. And so there was a correction proposed by Aberstich, Nui, and Perrin. 22, which says essentially that you add the conditioning of the expectations of the sample to the success event in which the sample looks good. And this is the bound A of that. Okay, so now let's look.
If your function belongs to, function f belongs to Vm, it's 0 on the right-hand side, right?
Exactly, so this is quite important. If f is already in Vn, the error is 0, so we should achieve exact reconstruction. We need to project functions on Vn.
But how it could be done? It's impossible.
You have sufficient information because you have m data points, and m is larger than n. So if f is in Vn, then you know exactly the coefficients of f. But the main point here is that even when f is not in the space Vn, but close to it, then the reconstruction is still good, which means the projection error is small. Yep. And so yeah, this is some kind of a stability estimate for approximation in Vn. Okay, so now let's look at what happens with the reconstruction that is used, and it's the same in both algorithms, and it will also be the same for us. It's based on weighted least squares. So f tilde will be taken as the minimizer over functions in Vn of not the L2 norm, because we would like to compute the projection in L2, but we don't have access to integrals of f. So instead of L2 norm, we take an empirical norm, which I'll denote with m because it depends on the number of samples. But that's what was denoted the L2 norm with respect to x by Egor Kozef, I think, in this talk. Okay, and this norm is defined as just the sum of squares, v of xi squared, with some weights wi. Okay, so here we need to design a random sample x1 to xn. Also choose some weights, wi, positive weights. And this will give the projection, and then we just find the least squares projection f tilde, which will satisfy, after some conditioning, the above error bound. Okay, and how to compute this f tilde? Well, it's essentially a linear problem, least squares, and it involves the Gram matrix of the sample. So if we take phi1 to phi n, an orthonormal basis of Vn, basis of Vn in the L2 norm, then we can define the Gram matrix G equal essentially the empirical inner product of the orthonormal basis function, so phi j, phi k, in the empirical semi-inner product associated to the sample.
About the weights, how you choose the weights, because they're depending on the points. Probably.
I'll come to that. The weights will depend on the points, and so as the points are random, the weights will also be random, but essentially just depending on the associated points. That's what. The two things that we have to figure out here is how to choose the points, how to choose the weights. And here, I'm saying that everything can be expressed in terms of this Gram matrix, which can also be rewritten as just by developing the inner product as a sum of the wi phi of xi, phi of xi transpose. And here phi is a vector whose coordinates are phi1 of x, phi2 of x to phi n of x. So this is a vector, it's transposed, and so here we get a rank 1 matrix, and we're taking a sum of rank 1 matrices, so G is some matrix in n times n. Okay, and the main point of this is that it characterizes the discretization that we have between the discretization inequality between the empirical norm and the continuous L2 norm. So that's the bound that we've seen already quite a number of times, that we can have a sampling discretization error for the L2 norm in terms of the eigenvalues of G here. That was shown in Anthony Lewis' talk, for instance. And here it's the minimal eigenvalue of G times VL2. Okay, and that holds for V in the space Vn only. And of course, we cannot expect to get such a bound outside of Vn, because well, here we only take a finite number of terms. Okay, this is quite immediate. In fact, if you look at the decomposition of V in the basis phi j, then here this L2 norm is just C transpose C, and the discrete, well, the empirical norm is just C transpose GC. Okay, so you see that you can pull out the matrix G with minimal and maximal eigenvalues. Okay, and so now we have some picture which says with this universal discretization property, as we have talked about, and many authors here have studied this, we get some equivalence between L2 and empirical norms. And now the picture goes like this. So we just want to bound f minus f tilde in L2, and I put a square. And let's draw a little picture. If Vn is the line here, the horizontal line, and f is somewhere here, then P Vn f is the orthogonal projection onto Vn. Okay? And f tilde is somewhere in Vn, but not the orthogonal projection.
Excuse me, but you a priori knows your basis.
Okay, here we fix the basis, and for
You know it.
computational purposes, we assume that we were able not only to have access to a basis, but to orthonormalize it. Okay. So that's for the analysis. In terms of computing the approximation, any basis would do, not necessarily orthonormal. And we would just have to solve the least squares problem associated to the basis, and the solution would be the same. So this is for the orthonormality, is for the analysis. Okay. Okay, so that's the picture we have, and essentially we're trying to bound f minus f tilde. We can apply Pythagoras to decompose this. So the first term is exactly what we want, f minus pvn f, the optimal error, and the remainder term is inside of Vn. But on Vn, we can change from term of norm, and instead of going from L2 norm here, we go to this empirical norm. And in the empirical norm, the picture is a bit different. We still have a space Vn, we still have a function f, but now f tilde is the orthogonal projection for the discrete norm. Okay, and Pvn is somewhere else. Okay, and so we translate this into this just by using the matrix G. And here, well, this part can be bounded by f minus Pvn of f. So that means, and we have lambda min of G to the minus 1, and the residual, but in the empirical norm. Okay? And there's one last step remaining, which is to bound this by an L2 norm. And we said that we were using random bounds. So what we're doing here is just taking the xi drawn according to some density times mu. Remember that mu was the initial density, and here we consider the initial measure, and we take a density over it, and we take Wi proportional to the inverse, 1 over rho of xi. So that the weights compensate for the distribution of the points, and in that case, the expectation of this is exactly f minus PVNF in the L2 norm. So we come back here with the expectation. Yep.
The inequality that relates the empirical norm and the L2 norm is only valid.
Is only valid in Vn. Yep. And here we were applying it to PVNF minus F tilde. So the difference which is in Vn. That's why we decompose this way. Okay. A few remarks here. Essentially, we only use the lambda mean part. So one-sided discretization. The other part won't be used in the analysis, but it's still useful for numerical stability purposes, studying the speed of convergence of, the algorithm and stability to errors. Okay. The other thing is that what is left here is that the constant C we had in the bound is now 1 plus lambda mean of G minus 1 to the minus 1. And I cheated a bit because I forgot about the conditioning step. But what should be controlled is the minimal eigenvalue of the Gram matrix. And for that, we still have some freedom in choosing the density of the points. Okay? The main observation by Cohen-Migliorati was that G, the Gram matrix, converges to the identity with some matrix concentration inequality as m tends to infinity. But we want the number of samples to be as small as possible, again, because evaluations are costly in our setting. And so we want this convergence to be as fast as possible, and this is fastest when, for IID points, when we take a density rho of x equal px transpose px over n for normalization, which is the inverse Christoffel function. Inverse Christoffel. Okay, and that's it for the theorem. We've chosen the density, drawn points according to the density, weights inversely proportional to this density. We obtain some concentration bound of G towards the identity, so we can bound in probability the lambda mean of G to the minus 1. We wrap it all together and we get a theorem.
But you need to use some result got it before.
Sure. So there is a technical part which is the concentration inequality, and you have to quantify it. And the results that were used are from Trop and before by Alswed and Winter, but you can use any type of concentration inequality for matrices. And
This first was Rudelson who got.
Okay. So Rudelson got one. There is one by Oliveira, which is adapting on Rudelson. There is one by Mendelssohn and Pajor, and there is a one by Trop. Plenty of them, all saying approximately the same thing. And this is the main technical tool. But I will not go further into the random IID setting, because what we're interested in is to reduce the sample size. You see that here m, the number of samples, is of order n log n, and that's necessary when you take IID random points to start with. Okay, and then there are methods to reduce the sample size based on an initial sample. Some were proposed by Abertis-Perrin. And one result is that, with Albert Cohen, we can essentially subsample from this random sample. And so for m larger than some constant Cn, we could get expectation of f minus f tilde L2 squared smaller than the constant and the optimum. Yep. and here it's subsampled points. Subsampled points. Okay. Well, some constant here, let's denote it C prime. And well, essentially the approach is to take start with random points and then remove the ones that are useless. If 2 points are close to one another, then evaluations of the function are these 2 points are similar. So we can remove one of the points and it doesn't matter for the approximation. Doing something like that, we can reduce the sample size from well, log linear to something linear. The problem here is that the constant C and C prime are quite large. So C and C prime are in the thousands or even tens of thousands. And in addition, the sum sampling strategy is not algorithmic. So it uses some complicated linear algebra from Marcus, Spielmann, and Srivastava, which we don't know how to compute in practice. And so we had some improvement recently with Abdelhaj Kifa, and this is the result I'm going to be talking about in the rest of the presentation, which is that for any m larger than n, and here there is no constant at all, we can get a bound of this kind, f minus f tilde, bounded by, again, C prime times f minus PV and f. But C prime now behaves, well, depends on m and n. And you can guess that when m is very close to n, the constant will not be that good. Still, it's 1 minus square root of n to the minus 1 over m. Okay, so the constant looks a bit complicated, but there is a 1 coming from the first Pythagoras, always the same, the optimal part. And then here there is something that explodes as m gets close to n. So here it's n above, n below. So this fraction is smaller than 1, which makes this positive, and so you do get a good bound. So let me give some examples. If we take m equal to 4n, or well, 4n to the minus 1, the n minus 1 is actually helping us here, we obtain C prime equal to 5. Okay, very reasonable constant. For m equal to 2n minus 1, C prime is something like 12.7, so still reasonable. And an interesting aspect of this result is that we can even go to m equal to n, which is not more least squares but interpolation. So here, the sample size is exactly the optimal, the dimension of the approximation space, and we still get an error bound in expected L2 error with C prime equal 1 plus 4 times n squared. So of course, it goes to infinity as n goes to infinity. You cannot expect here some bounded constant for interpolation, but reasonably fast. Okay. Yeah, perfect. So this is the main result I'm presenting, and now I'll go a bit into the algorithm. So how did we go from IID random points to something a bit well, refined algorithm, which does not have this log factor in the oversampling. And well, some parts of the algorithm are common to what we had before. Yep. Good job. So one part that is kept the same is that the xi are drawn according to some density times mu. But here, the density rho I depends on I. Okay, so they're not IID because the density of point xi is not the same for all I. And again, the wi are proportional to 1 over the density at point xi. Now it's rho I of xi. But the question is, which density do we take for sampling the point xi? Well, and you saw that in the IID case, the good option was to take a density which was a Christoffel function, phi transpose phi. Well, now we'll be taking rho I of x to be something, well, proportional to, it's up to a constant, phi of x transpose phi of x again. But here, instead of putting just the identity matrix, we put some function of the Grumman matrix, the partial Grumman matrix. That is the Grumman matrix computed from the previous points. So Gi is the sum for all the previous points, the one we have drawn already, well, of the Wk phi of xk transpose phi of xk. So this is typically an adaptive algorithm, as we have discussed them. The sampling density for the point xi depends on the choice, the previous choices of x1 to xi minus 1. Yep.
But they do not depend on f, right? So it's not adaptive and wouldn't. Just to be clear.
Ah, okay, right. It does not depend on the function f. Yeah, that's important. Okay, so yeah. So not adaptive in your setting, just adaptive in the way I wrote it. Sure. So in the end, we're drawing all the points, and then we can evaluate the function values afterwards. Okay, not adaptive then. Okay, but still it's written in a greedy fashion. Let's try to understand what this is, and in particular, what is the function f that we're putting inside. So f is some function that sends the Gram matrix to some other matrix. Roughly speaking, and that's some approximation, f of g will look like g minus li to the minus 1, so g, the Gram matrix, minus some scalar times the identity to the minus 1. Let's draw this. If you consider, so gi is a semi-positive definite matrix with some eigenvalues. So lambda 1, lambda n are the eigenvalues of gi. Okay, and essentially the function f just applies to all eigenvalues, well, to all eigenspaces of f almost separately. So you can somehow plot f of lambda, which will be something like a hyperbola with, okay, L, the lower bound on the eigenvalues, and then some sort of potential. What is the interest of doing that? So here, what we're saying is that f of g is putting more weight on the eigenvector associated to the smallest eigenvalue, and less weight on the eigenvalue, the largest eigenvalues. So the eigenvectors associated to the largest eigenvalue. So when drawing the point xi, we will increase the probability of drawing some point x that is that interacts with the smallest eigenvalue of gi. And so this will encourage the new contribution. Here, gi plus 1 will be gi plus wi phi of xi transpose. The new contribution from gi to ji plus 1 will most likely be close to the minimal eigenvectors of gi. And so we expect that the smallest eigenvalues are increased more, or at least as much as the other eigenvalues of gi. Which means that by iterating this algorithm, sampling all the points, we'll push all the eigenvalues of gi together, and in the end, after m steps, so after having sampled m points, all the eigenvalues will have moved away from 0, and lambda mean of gm will be large enough in a controlled fashion. Okay, and well, one useful aspect for this. Now I need to erase something. No, I'll go to the next. Sorry. One useful thing here is that we saw the gram matrix G was a sum of rank 1 matrices, and here we're just making a rank 1 update. So in some way we can control the eigenvalues of Gi plus 1 based on the eigenvalues of Gi. And for that, well, we just use some linear algebra tools like the matrix determinant lemma. Which says that, well, the determinant of G plus A transpose is determinant of G times some correction, 1 plus A transpose GA. Okay, what does that mean? If we know G, so here the gram matrix at the previous step, or essentially, well, with some shift, the roots will be the eigenvalues. Then we can update the formula, the characteristic polynomial, and solve it for computing the eigenvalues at the following steps. So in this way, with some potential that looks like this function, we do have some control on all the eigenvalues of the gram matrix at once. And that's, well, the main linear algebra tool for this algorithm, which was already introduced by Batson, Spielmann, and Srivastava in 2009. And the main point here is that we made a random version because we still need the expectation here, expectation of the empirical norm to be close to the L2 norm. And to do so, we sample the point at random and we do some, well, randomized versions of these linear algebra tools. Okay, so that's for the algorithm. And now I'll just make a comparison to another method, which is quite used for sampling, well, random points, especially in interpolation. So in the case m equal to n, we have determinantal point processes. And I'm going to argue that essentially these fit into the framework that I just presented with some different function capital F. And so here, well, the sample x is x1 to xn because we took m equal to n. And this will be drawn according, we have already seen this, to the design matrix phi of x. And here this is a square matrix because we have as many sample points as basis function squared times the nu to the n. Okay, and Anthony Nui already said that this sampling density can be decomposed as the marginal for the first point and then the marginal for the second point conditioned to the first point, and that's exactly a greedy way of seeing the sampling as I presented there. And here, well, for this DPP, the function f that we're considering is just the projection onto the image of G orthogonal. So what happens here? We have m, well, the number of samples is n, so during the steps of the algorithm, we will be with I less or equal to n, which means the matrix Gi will be of rank at most I. Okay, so we start with G0 is the empty sum, so it's 0, and then at some steps we have something like n to the minus I 0 eigenvalues, and then the other eigenvalues of G are here. Okay, and what is this function f that we're using? It's just 1 on the null eigenvalues and 0 on all other positive eigenvalues. So you see that it fits into the same framework, but essentially here it's a sharper function with a jump, 1, 0. Whereas there it's some kind of relaxation of the problem. So how does it compare? Essentially, I should be adding some references. the theorem for determinantal point processes. And for instance, it's written in a paper by Ayoub Beleji, who's here, Bardonnay and Chenet. And that's a recent paper saying that they had an interpolation bound in expected L2 norm with C prime equal 1 plus n. So here, determinantal point processes are doing better for interpolation. Instead of having the n squared, the C prime equal O of n squared, they have C prime in O of n. So for interpolation, they do work better. But when it goes to least squares, there's a problem. Because if you try to keep going on with that function f, after the n step, this projection is just 0, and so there's no more sampling density. Which means that it's hard to keep the information from the n first steps if we want to go further. Okay, and some alternatives have been proposed, like continuous volume sampling or iterated DPPs, determinantal point processes, by Nui and Michel, for instance. And that's also very recent. Yep. And essentially, the bound is not exactly as sharp as you would like them. So you get a bound with a logarithmic oversampling, and not the sharp bound that is written here. Okay, so there's a trade-off. DPPs are better for interpolation, and it's harder to analyze them. Also, they do work very well in practice, but it's harder to get sharp bounds for least squares. And why is that? Yeah, I'll try to be fast. After that, essentially, when you're using that function, you forget about the position of all the positive eigenvalues here. Where are lambda n and the other large eigenvalues? You don't care, you forget them, as long as they're positive. Which means that once you send all the eigenvalues in the positive part, you don't have any information left about where the eigenvalues would be. Whereas in the other part, for this Batson-Spillmann and Srivastav algorithm, what you remember is some average of the eigenvalues, but weighted by, how low are the eigenvalues. So the lower eigenvalues have more weight, but the large eigenvalues still have some weight, which is important to keep going and not to degenerate when m becomes larger than n. Okay, I should add something here, that f was approximately this function, but in practice what we took was a slightly different function, which is not necessarily semi-positive definite, and it might even be negative for some eigenvalues. And so what one should do is put some positive part. So it's quite interesting that we're able to sample according to the positive part of some density, and that the analysis can still be carried out. Okay, I have 1 minute left, and still a short part I wanted to go about. And this part is saying, what about, deterministic bounds? Because here, all the results are in expected L2 error, and also you can obtain results in high probability. Maybe that's not satisfactory. And we said that when the error on the right-hand side was in L2, you could not get anything better. But you can get a uniform bound. If you take the optimal error in L2, f minus p. Okay, and here you take the optimal projection for the L-infinity norm of f into Vn. Consider in L-infinity norm with some constant C prime, C prime. And here you can get something like that. So here, deterministic, but still L2. And on the other side, it's L-infinity bound. Okay. And essentially, this result was already obtained earlier by Vladimir Temlyakov. together with Limonova. Well, it's 2 different papers, and also by some improvements by Bartel, Schaffer, Ulrich, in which they could remove the weights and do least squares instead of weighting least squares. This is Tino Ulrich. Yep. Okay. And okay, essentially they obtain bounds of this form. Yep. And what we're saying here is that the same algorithm that was used for randomized approximation can also be used for uniform approximation with a minor correction instead of taking the positive part. So here you replace psi plus the positive part by max of psi with some threshold delta positive. Okay, and I'll stop here. There was one last thing about obtaining bound in L infinity, but David Krieg already spoke a little bit about that, so we already obtained, somehow obtained similar bounds, but that's it. Thank you.
Thank you. Go for some quick questions.
But in the paper by Watson and co-authors, there is no estimate of largest eigenvalue. Could you get both estimated, lower and upper?
Yeah, sure, we can. So in Watson, Spielmann, and Srivastava, the analysis is carried on not only with the lower bound on the eigenvalues, but with some upper bound on the eigenvalues, and then you look at the function that also increases. Okay, it's a potential. So you essentially bound the eigenvalues from above and below, and this yields the discretization inequality with the 2-sided one. Okay, now what we're saying here is that for the upper part to come back from empirical norm to L2 norm, what we need in the randomized case is just an expectation. And so we do not need in practice a sharp lambda max upper bound. We still get one, but with a factor n, essentially.
So it's not sharp.
Okay, it's not sharp. We could make it sharp, and essentially what would happen then is that the density you put takes into account both lower barrier and upper barrier, and so the sampling density is not as good for increasing the lower eigenvalue. So half of the sample points essentially are used for increasing the lower or upper bound, half of the minimal eigenvalue, half of the points are focused on not increasing too much the upper eigenvalue. That's very hand-wavy, but what it means is that with that you would need to take n, the number of samples, to be of order 2n. And you can improve this, but then the constants, the C prime, becomes much uglier. So it's possible, but more difficult.
Very short question.
What you can say about noisy data?
Yep, so noisy data. It's kind of the same question. For noisy data, you need control on lambda max. And so the answer is the same here. We don't have stability, but stability with a factor n, which is not so good. And if you want a better stability property, you need a 2-sided Watson-Spielmann-Srivastava algorithm, which is trickier.
Okay, so very short.
I'll try. If I understand, so have you considered like the hierarchical approximation problem? So now you have a sequence of subspaces P1, P2, P3, and you want to be able to recycle your sample points. So
we're not exactly there yet. Here, the space is fixed once and for all, and the algorithm is greedy, but it also has some dependence on the final size. Essentially, there are some parameters in the function f that depends on the final size of the sample. And we're almost at a hierarchical method and trying to do that.
okay.
Thank you again.